Things are going to get a little bit weird in the video today because we are going to be discussing the two phenomena that are both related to light that really threw the world of physics on its head back in the early 20th century, late 19th century. These two phenomenon really showed the world that classical Newtonian physics did not work for everything. They work really well for certain things, and other things they don't work very well for. So the two phenomena we're going to look at are called blackbody radiation and the photoelectric effect. So the first one here, blackbody radiation, this is the phenomenon where everything, no matter what it's made of, if it's made of matter, regardless of the elements that it's made of, everything gives off radiation, and that radiation is determined, the kind of radiation or the wavelength or frequency of the radiation is determined by the temperature of the thing. So high temperature materials give off light that is in the visible spectrum, and colder things give off light that is in the lower energy, higher wavelength, lower frequency radiation. So if you've ever heard of things that are red hot or white hot, things that give off temperature simply because they are hot. So lava is an example of this. The heating element on your stove, if you have an electric stove or oven in your house, the reason that those things glow is not to warn you, hey, this thing is hot, don't touch it, although it's kind of a nice side benefit that it essentially works as a warning sign to don't touch this. It's not a built-in safety measure. That is actually glowing because it is hot. Everything glows. You glow. Right now, you sitting in your chair, or wherever you happen to be, you are glowing. You don't have to be pregnant to glow, although interestingly enough, you do glow at a slightly different wavelength if you're glowing, or if you're pregnant, because when you're pregnant, you actually, I believe your body temperature goes up slightly, if I remember correctly. You have a slightly higher body temperature, which does mean that you actually glow at a slightly different wavelength than everyone else, but that is besides the point. Everyone glows in the IR spectrum. Every person, based on our temperature, we glow in the IR spectrum. But everything in the universe glows at one wavelength or another, just depending on their temperature. This, by the way, is how heat, like goggles that can see heat, like night vision goggles, or goggles like or satellites. If you've seen, like in some of the movies, they'll have satellites that can see people, like people glow in the images. Those are actually detecting body heat, and the way they detect body heat is using blackbody radiation. They're looking for that infrared radiation. So when this effect has been known for a very, very long time, obviously, like even back in the hundreds of years, just 200-300 even older, like way, way back, you would have blacksmiths that would, they would take metal and they would form it into swords or horseshoes or whatever. And when they would do that, when they would heat the metal up, it would start to glow. And so this effect has been known for literally thousands of years. But it wasn't until the early 20th century that people tried to actually explain why blackbody radiation is a thing. And when they tried to explain blackbody radiation using classical mechanics, using Newtonian physics, what they realized was that classical theory, the Newtonian physics, did not match what they actually observed, like at all. So the black line here is using Newtonian physics, what the radiance, how much light is being given off at certain wavelengths. if something was at 5,000 Kelvin, which is really hot. Don't get me wrong, it's really, really hot. And so you would expect something at that temperature to give off a lot of light. But classical mechanics said it should give off even more than it actually does. So the actual amount of light given off by something at 5,000 K is this blue light here. Or sorry, the blue line here. So this is what we actually observe. And the black line is what Newtonian physics said we should see. This is obviously very, very different. Classical mechanics said that even at our relatively cool temperature, at 98.7-ish degrees, we should be giving off ultraviolet light. So everything, even at room temperatures, not even at 98.7, even at room temperature, things would be giving off ultraviolet light, which is crazy. Things do not give off ultraviolet light if they're at room temperature. This is what we call the ultraviolet catastrophe, where there is this very well-known but clearly misunderstood phenomenon that was taking place, where classical mechanics simply could not explain what was happening. So this was the first thing that kind of gave scientists an inkling that maybe we don't actually understand the way the universe works as well as we thought. The second thing is the photoelectric effect. So what this is describing is a phenomenon that takes place when you shine light on a metal. When you do that, electrons are going to be ejected from that metal. And there's two things that are noteworthy to notice here when this happens. The first thing is that the frequency of the light must be high enough to get radiation to eject electrons from the metal. So, since the light is transferring the energy to the electrons to allow them to overcome their attraction to the nucleus, the energy of the light must be related to its frequency. Essentially, you have an electron here, and it is inside the metal, and when you shoot light in here, and it impacts the electron, if the light doesn't have enough energy to kick the electron out, then nothing happens. So there's a certain minimum threshold of energy where if the light that you're shooting in doesn't have that minimum amount of energy required, the electron's just going to be like, I don't care, not going anywhere, staying where I am. And this was understood. This was true for classical wave theory. It's not something that was a big shock at the time. People understood this to be true. You have to overcome that attraction between the nucleus and the electron, and if you don't have enough energy to do that, then nothing's going to happen. The more interesting thing that was discovered was that the number of electrons that were ejected when you shine a light on a piece of metal is proportional to the intensity of the light, not to the frequency. So essentially there was some minimum amount of energy. And you can see that on the graph here. So the frequency of light is down here below. And frequency and energy are proportional. So as the frequency goes up, the energy goes up. There's some minimum amount of energy here. If you don't have light that is at least this energetic, nothing happens. But once you get past that, what they expected to see was that, okay, if this is the minimum amount of energy, where the light has to have this much energy to kick the electron out, if we go to 2 times that, we should see 2 times the number of electrons. Because we have 2 times as much energy, so we can kick out 2 times as many electrons. And that is not what they saw at all. What they saw instead was that once you got past that threshold, that minimum amount of energy, it just stayed constant, the number of electrons that were being ejected. So you would increase the frequency of the light, and you would still get the same number of electrons being ejected. The only thing that would increase the number of electrons excuse me, that were ejected from the metal was if you shined a more intense light. And the intensity here is not the frequency or the wavelength. It is just essentially a brighter light, more light. So if you had a brighter, higher intensity light, then you would get more electrons being ejected. So what this led Einstein, actually, he was the person that discovered this, and believe it or not, this is actually what he got his only Nobel Prize for. He did not get a Nobel Prize for his theory of relativity. He got a Nobel Prize for the photoelectric effect. He was able to take this information and realize that light is actually not just a wave. Light must be composed of particle-like packets. And so even when you had more than enough energy up here, if you got up to this point and you had 2 times as much energy to eject an electron, once that photon, which is what he called these, actually I think he called them quanta, but as he says here, so Einstein proposed that the light energy was delivered in packets called quanta or photons. When that photon of energy impacts the electron, if it has enough energy, it will kick the electron out, but at that point it's used up. That photon does not then go and, it doesn't give up half of its energy and then become a new photon with half the energy and go force something else to get kicked out. No, that extra energy usually gets released in the form of heat, but it does not kick out 2 electrons. Once that photon gets used up, it's used up. It's gone. So Einstein said that the energy of a photon of light is directly proportional to its frequency and inversely proportional to its wavelength. And that's just because the wavelength and frequency are inversely proportional. So the equation that he developed to quantify this is right here. And actually these 2 equations are the same equation because the frequency, which is the V looking, the nu again, I think that's the Greek letter, is equal to c divided by the wavelength. That's why these are just the same equation, just slightly differently written. This will allow us to solve for the energy of a photon. So this E here, this is the energy of 1 photon. Which most of the time is not terribly useful. More often than not, we're going to be dealing with moles of photons, but if we do that, then we just take the energy we get for 1 and just multiply it by however many moles we have to get that total amount of energy. But this equation is describing the energy of a photon of some wavelength of light. So the energy is directly proportional to that frequency. The constant that's thrown in here is what we call Planck's constant, and it is an itty-bitty-bitty number. But that should make sense because a single photon is not going to have very much energy. It takes a whole bunch of photons. Right now, you are being impacted by trillions upon trillions upon trillions of photons. And so if those photons had a whole bunch of energy, you would be fried. Excuse me. So it would make sense then that to get the energy of 1 photon, you would take a very, very, very tiny number and multiply it by a number that the frequency can be large or small. Just kind of depends. Depends on what the light is that you're looking at. All right. So the other key thing that comes out of this equation is that when we're dealing with energy, and that energy is in the form of photons, the energy can only come in amounts of integer values of this h nu, Planck's constant times the frequency. So if we have a source of energy, excuse me, where that source is giving off photons at a certain frequency, the only energies we can get from that source are integer values of this h nu portion here, because we are never going to have 1.5 photons. We're never going to have 1.11 photons. We can only get whole number increments of energy. And this is what we mean when we say that energy is quantized. When we have a source of energy and it's giving off energy based on this equation, the energy that we get is always quantized. There are only certain values of energy that are allowed. And we'll come back to that a little bit later. But for now, let's do a couple quick example questions here, finding the energy of some light. So the first one here, what is the energy of a photon of red light with a wavelength of 700 nanometers? Now, just for the sake of time here, that 700 nanometers, I know that we're going to have to switch that to meters. And if you remember from the last video, I think it was the last video, maybe 2 videos ago, when we're going from nanometers to meters, we can just take that nano out of the number and replace it with times 10 to the negative 9. And that gives us our wavelength in meters. And if you remember from the previous slides, the energy of a photon is equal to Planck's constant times the speed of light over the wavelength. So, the energy of this photon is going to be 6.626 times 10 to the negative 34 joules seconds. That is Planck's constant. And here it's shortened to 6.63. I learned it as 6.626. And then we're going to multiply that by 3 times 10 to the 8 meters per second divided by 700 times 10 to the negative 9 meters. So my meters here are going to cancel, and those seconds are going to cancel, which is going to leave me with just joules, which is good because that's a unit of energy, which is what I'm looking for. And so 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by 700 times 10 to the negative 9. Oops, I did something wrong with my calculator. Let's try that again. That times that. Oops, that might have been the problem. Divided by that. Okay. So, I get 2.84 times 10 to the negative 19 joules. And that is for every photon. Joules per photon. Okay, go ahead and pause the video for just a second and try to do the same thing here again, but now with violet light. Alright, you might have noticed if you tried to do this yourself that really the only thing that's changed here is we're going to have 400 instead of 700. Everything else is exactly the same. So the energy is going to be 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 8 meters per second divided by, oops, not 700, 400 times 10 to the negative 9 meters. And so if you do everything else the same there, and you just use 400 instead of 700, what you get is 4.97 times 10 to the negative 19 joules per photon. Which, if you notice, is larger than the red light. So the violet light gives us more energy per photon than the red light, and that should make sense because violet light has a higher frequency. It has a lower wavelength, which means it has a higher frequency, and so it will have more energy per photon than the red light. And that is a extremely tiny amount of energy per photon, but again, photons are extraordinarily tiny. And so a single photon is not going to have very much light at all, but again, you are being bombarded right now with trillions upon trillions of photons. If you go outside and stand in the sunlight, it's quadrillions upon quadrillions of photons hitting you, and those will warm you up pretty fast. Because that many photons, even with that tiny amount of energy per photon, you can get a decent amount of energy if you sit out there long enough. So, in summary here, the energy of light is quantized, so therefore it must have discrete energy values. There are only certain energies of light that are allowable. Energy is proportional to frequency. Light has particle-like nature, not just wave nature. It has both, which is going to lead us into particle-wave duality, so we'll talk about later. And a single photon is the smallest packet of light, and we can describe the energy of it using this equation. Right, and the next one, we'll do this next practice problem here, and talk a little bit more about how the energy of light and the frequency of light are related to each other, and then jump into particle-wave duality. So I will see you in the next video.